All right. Hello, mathematics fans, geometric analysis fans. If you are just a regular YouTube denizen and this video has been recommended to you, or if you found it somewhere and you've clicked on it, then welcome. I'm going to be talking about some research level mathematics, and it's not supposed to be scary. This is a series of talks as part of the Geometric Analysis Festival. We are very inclusive and we are going to try to make our talks as accessible as possible. Let me tell you a little bit about what I'm going to be talking about. So basically imagine you have something like Jacob's ladder. So you might have been to a science museum. You know, you have these kinds of two metallic rods. These are just pens, but anyway, metallic rods, and a little electric arc comes up and out of these two rods. And if you can imagine that little arc as a curve and this in a flat plane, then that's similar to the geometric situation that I'm going to be considering. It's not similar in terms of the actual equations, but geometrically it's similar. Except in my case, for these series of talks, we've got parallel rods, parallel lines. Okay, so what am I going to be doing? I'm going to be talking about some research level mathematics, but yes, like I said, please don't be scared. I'm going to make these videos short. I'm going to try to do them in detail. So perhaps I will need to make a few shortcuts here and there, but if I do anything like that, I will tell you. I'm always going to be honest with what I'm doing. I'm not going to try to hide or deceive anything. Now that means that these short videos may end up great in number, but I think that's a fine price to pay. So I don't know how many we'll make. I don't know how many I'll make, but this is the first one, and that's the plan. I'm also going to do it old school. I've got this picture of a blackboard behind me. I'm not going to write on a blackboard, unfortunately, but I will just create the mathematics, or at least the talk, as I'm going. So if you want to take notes as well, please feel free. And if you have questions for anything that I'm going to talk about, how about I give you my contact details, or I will try to stay on top of comments, but I'm not sure how feasible that is. So my name is, hopefully you can read this, Glen Wheeler, and my email is this. This is my work email, Glen with one N, at uow.edu.au. Okay, if you want to ask me any questions about anything that you see in these talks, or anything really math related, shoot me a line, drop me a line, whatever, shoot me a message, and I'll be really happy to have a chat. Okay, so another relevant name is Valentina Wheeler. So let me write her name here. I'm not going to give you her email address, but if you want, you can Google it, because we are, after all, in the public domain. Okay, this is Valentina Wheeler, and Valentina is my collaborator on this project, so credit goes to her, and I would like to thank her for all of her help. Okay, so what am I talking about? Here we go. I'm going to do a title. Basically, what we're going to be doing is focusing on a question called stability. All right. And now in mathematics, when we prove things, we call them theorems. So stability theorems and the actual equations that I'm going to be talking about are the curved diffusion flow, which I abbreviate to CDF, and the other equation I'll talk about is the free elastic flow, FEF. Don't worry, I'm going to say these names many, many times, so you have lots of chances to remember them. And now, because we have this geometric situation where we have two parallel lines, two parallel rods, we call it on, and I'll just draw parallel lines for the word parallel. And because our background space is the plane, we say in the plane. All right. So I wonder if I can use the power of technology to draw a straight line. You know, I always have trouble drawing straight lines. Here we go. Look at this. That's a pretty serious line. Can I even skip the P? Nice. All right. As you can probably tell, I'm just learning with this stuff, so please give me a break if I mess it up. Okay, so what's the rough outline for these talks? I'm going to break it down roughly as follows. In the first group of talks, or the first talk, I think it'll be a group of talks. Each of these will be groups. I'm just going to introduce the problem and give some challenges, explain some challenges with difficulties with trying to actually do what we're planning to do, to prove out what we're trying to prove. Key challenges. Okay. By the way, stability is, this word stability, what it means is that if you have, say, for example, a physical system and it's in equilibrium, so let's think about, imagine you have a bowl, just a bowl, like a dinner bowl that you would eat a soup out of or something, and you put a circular ball in the bowl. Then this is a stable situation, because if you push that ball around, if you perturb it slightly, it will just return to where it was before. We call that a stable equilibrium for the system. And that's what we're going to be trying to do, is to figure out if a straight line like this between our parallel lines is stable or not. You know, and how much can you push it? You know, can you really just wreck this line and make it oscillate, make it self-intersect and things, and will it still straighten out? Probably not. No, it doesn't, but it's all difficult. Okay, after we've given a bit of an introduction, we're going to talk about something called a priori estimates. A priori just means before. So these are estimates that we can do that control the geometry of the evolving curve, this little arc, pretty much before it starts evolving. So things that we can control for free, so to speak. And I'll try to do these in general, but some of them will be under a curvature condition. So I'll explain what that is in a minute. And that's the focus of the third section, which is what we call global analysis under a curvature condition. Right, so what is curvature? Curvature is a measurement of how bendy something is. If it's bending a lot, you know, it's going right back onto itself, it has a large curvature. If it's like a straight line, it has zero curvature. That's pretty much all you need to know to understand what I'm saying. What I'm saying here is global analysis means long time in the future. So if you let this arc relax, flow according to its equation, and you wait a long time, that's global. Global in time. And the curvature condition is a restriction on the initial curve. So like we were talking about with the ball in the bowl, this is a restriction on how much you annoy that ball. You know, did you really smack it and shoot it off? I mean, if you shoot it outside the bowl, it's probably not going to come back. And that's really what we're talking about. You know, how big is this bowl? You know, how much can we move it? And this curvature condition is really giving you a very precise answer to that question. Okay. The last section is going to be on convergence, which is the final, you know, cherry on the cake, so to speak. Even though I don't even like cherries, so no, don't like cherries. Convergence, and some, to finish off, I'll give you some conjectures. All right. I can see that we've already gone for 10 minutes, so I'm going to cap off the first one here, and I'll start up again where I'll do less writing and more picture drawing. And I'll talk about some things that we know already and what we can expect. Get on to the first section, Introduction and Key Challenges. All right. Thanks for listening. This is me signing off. Take care of yourselves. Peace.